All right, so let's look at some plots that I made in Desmos. I really like Desmos. I don't know if anybody's ever heard of it. Probably a lot of you have. It's a graphing calculator that's online. I definitely recommend checking it out. That's what I use to plot this function. So of course, this is just a very basic linear function. Y is equal to x, right? So my x-axis, I'm looking at a value of 1. I get y is equal to x, so the y value is also 1. X is equal to 2, y is also equal to 2, and so on. And so I get this linear plot, right? The slope of 1, whatever x value I go to, that's going to be my y value. Okay, so that's pretty straightforward. So what happens if I plot a logarithmic function with linear axes? Well, this is what we see. So now I'm plotting the log. This is definitely the log base 10. Anytime you just see log, it's inferred that the base of the logarithm is 10. So right, we were writing log base b of x is equal to n, right? That's what we had. I think that's what we had in the slide. Let me go look real quick just to make sure. Log base b of x equals to n, and that, corresponds with b to the power n is equal to x, right? These are basically interchangeable. Not interchangeable, sorry, but they're inverses of each other. And so here we don't see the base, but if you don't see the base, you should assume that the base is 10. So I can come here, super pixelated, and just write a little 10 in there for us so that we can have that. But just assume if you don't see the base, then the log function is log base 10. Okay, so in this case, log base 10 of x is our function. So if I go to the log base 10 of a value of x is equal to 1, right? What is that saying? It's saying 10 to the what gives me 1, right? And so if I'm looking at a value of y equals 0 there, that means that 10 to the 0 is what would give me 1, right? And so if I move out to a value of 10, right, at a value of 10, x equals 10, I'm right here, right? Log base 10 of 10 is my y, right? And that's saying 10 to the what is going to give me 10. And that's a value of 1. So my y value here is 1. And so you can see that this thing grows really, really, really slowly. Logarithms are known for being functions that grow very slowly on a linear axis. Why? Because now the next value is 2, right, which is here. That's not going to happen until x equals 100, right? X has to go all the way to 100 before y is going to be 2. And x has to go all the way to 1,000 before y is going to be 3. And then 10,000 before y is going to be 4, right? So this function grows incredibly slowly on a linear axis, right? But what happens if I move the logarithmic function, right, y is equal to the log base 10 of x, over to a logarithmic axis? This is what happens. Now we see linear behavior because my axes are scaled to be logarithmic, right? So at a value of, I see my value of 1 here on the y-axis for an x value of 10, which we saw previously, right? That was the same thing that we saw here. For x value of 10, my y value is 1. Over here, same thing. But because of the way that the axes are not evenly spaced, right? My axis is logarithmic. I get this linear looking plot, which is very nice. It's very easy to sketch. This behavior is not so easy to sketch. This behavior is very easy to sketch. It's just a straight line, right? And the same goes for the value 0.1, right? What does the value 0.1 mean? Well, it's log base 10 of 0.1 is negative 1. What does that mean? Well, I know that base 10 to the what, right? This question mark here gives me negative 1. It gives me 0.1. That's saying that this value here is negative 1, right? Well, that's the case. 10 to the negative 1 is equal to 0.1. If you recall, because basically x to the minus n is the same thing as 1 over x to the n. So 10 to the minus 1 is the same thing as 1 over 10 to the 1, which is 1/10, which is 0.1. So that checks out. And so the key takeaway here is that I can get logarithmic functions to look linear on a logarithmic axis. And we've already talked about how frequency response ought to be plotted on a logarithmic x-axis, because logarithmic x-axis allows us to view a very broad range of frequencies, right? I think that might be the next point that I make here. Yeah, exactly. A linear axis allows this. I'm looking at the same exact size plot here, right? I'm looking at 0 to 10 in the y direction in both plots. But look at the same size plot. Here, I can only view values from 0 to roughly 12 on a linear x-axis. With a logarithmic x-axis, I can view from 1 all the way out to 100,000 on the same size plot, right? And so this is great for frequency response, because in electrical engineering, we often want to view broad ranges of frequency like this to see how our signals and our circuits are going to behave over the broad range of frequencies that there are in electronics. You can have DC signals, which would be way down here at 0. You can have hundreds of megahertz, which would be way out here, and I can view them all on a single concise plot if I just use a logarithmic x-axis. But the problem is a logarithmic x-axis makes things difficult to plot. But if I don't just plot a linear function, but instead I plot a logarithmic function on a log axis, then things become easy to plot again, because now I get linear behavior. And so that is the reason why, coming back, my dBs are necessary for a frequency response plot. I already have my logarithmic x-axis. I need a logarithmic y-axis so that I can get plots that look pretty linear most of the time, that are very easy to sketch by hand. And this is a very powerful tool for analyzing frequency response, and we're going to derive where and why the decibels are, or where they come from and why they're used, in the next couple of videos. I don't know if that's exactly what I have next. Let's see. Yep, what are dBs? That's going to be the next one. So for now, we've discussed the logarithmic axes, we've discussed the logarithmic functions, and the key here is that we're basically going to take the data that we already have been plotting, which is this data here, and we're going to map it to a logarithmic function so that we can get something nice that's very easy to sketch with just straight lines. And that is what a Bode plot is, okay? So this has all just been motivation for what the Bode plot is and why we want to use it. Why do we need to make it logarithmic? And we're going to see all that in the next video. So I'm going to go ahead and end this video, and the next video is going to discuss what are dBs. And from there, we'll be comfortable with the Bode plots and starting to sketch them and analyze them. Okay, so I'm going to end this video right here.